In the second part of this presentation, we'll talk about heat transport with open loop systems in a bit more detail. The first thing to notice is that energy and mass transport are decoupled. We transport the groundwater by pumping, moving it through the plate heat exchanger to exchange energy, thermal energy with the building, and the thermal energy is exchanged due to temperature differences. So the relationship between the temperature difference and the volume flow rate will give us the capacity on the plate heat exchanger. In the aquifer itself, the groundwater moves through the pressure gradient caused by the pumping. What is important in this respect, is the diameter of the filter and the length of the filter. We want to limit the maximum velocity on the filter wall to prevent clogging of the filter due to the fines in the aquifer that are moved due to the pumping. If the water velocity is too high, we get too many fines going to the filter wall and the filter will clog, will not be permeable to water anymore. To calculate an open loop system, to design an open loop system, a few aspects are of further importance. For instance, the calculation of the hydraulic and thermal influence zone. We do not want the cold well and the warm well to interact too much. In the picture on the top right, you can see that there is some deformation of the warm and the cold well due to the fact that they are relatively close, because of course the distance between the wells can be limited by the available area that we have. A rule of thumb is that we would like to have a distance of at least 2.25 times the hydraulic radius or 3 times the thermal radius of the well. And the thermal radius is usually taken as the 0.5 degree temperature change line, or the 0.5 degrees isotherm. These calculations can be done with either an analytical or a numerical model. Example using analytical models, fairly straightforward equations where the hydraulic radius is a function of the total volume of groundwater pumped, the total volume of groundwater infiltrated, and the porosity of the aquifer, for instance 30% porosity, and H, the filter length, for instance 15 meters filter length. So plugging these values into the equation, we get a hydraulic radius of around 53 meters. The thermal radius can also be calculated. That of course includes the thermal capacity of the ground and the thermal capacity of the groundwater. The heat capacity of water, 4.2 megajoules per meter cube Kelvin, and the heat capacity of the ground, 2.5 megajoules per cubic meter Kelvin, at least for porous media in the Netherlands. Plugging those values into the equation, we get a thermal radius of 38 meters in this case. Another aspect is the natural groundwater flow. The natural groundwater flow can affect the functioning of the open loop system by, transporting away the stored heat and the stored cool. So the natural groundwater flow is usually expressed in Darcy groundwater flow, where you can see this in the little graph on the right. We have an aquifer at depth with a separating clay layer on top and a second aquifer on the top. The wells are installed in the second deep aquifer, which in this case has a artesian water table at H1. You can see there that the water table is slightly above the surface of the ground, and H2, it is well below the surface of the ground. So we have a difference in pressure height between H1 and H2, a difference delta H of pressure or of water level. The distance between the two wells, delta X, then allows us to calculate the groundwater gradient. If we also know the hydraulic conductivity of the aquifer, then we can calculate the Darcy groundwater flow, which is a measure of the total volume flow through a surface of 1 square meter in the ground. The formula is given below. It is actually minus K times the groundwater gradient. Now, this tells us how much water flows through a surface, but it does not tell us how far a particular water particle will travel. To be able to calculate that, we need the effective groundwater flow, which is the Darcy groundwater flow divided by the porosity. So with a porosity of 25%, the distance traveled is about 4 times the Darcy groundwater flow. Of course, we have to take into consideration that this is all valid for porous geology. If we have fractured geology and not porous aquifers, it becomes much more complicated. At the big scale, we can still work with averages, but on the local scale, we need to consider more probabilities in hitting fractures or not hitting fractures. So the effect of groundwater flow, natural groundwater flow, could mean that the aquifer is less suited for a storage application, and or it can, let's say, affect the way in which we want to position our wells. For instance, if both cooling and heating are equally important, we would like to position the wells perpendicular to the groundwater flow. On the other hand, if cooling is dominant, we want to have as little contamination of the cold aquifer as possible, and we will position the cold well upstream of the warm well. Obviously, in reality, designing an open loop system is much more complex and really work for specialists, but this will give you a good general idea of the functioning and heat transport in open well systems. In the next part, we'll look more at closed loop systems.